Hi, my name is Spencer Kirkham, and this is my final project for mechanical design. Alright, so as you can see here, this is the cover page for my project, and the topic of the project was the design of a shaft under dynamic loading. So our goal here was essentially to analyze dynamic loads that are acting on a shaft. We looked at the shaft diameter and how we could optimize it, and we also looked at maximizing the factor of safety with and without the design constraint. So I started first by listing equations that were used to calculate the maximum factor of safety. I began by finding the mid-range and alternating normal and shear stresses, which are right here. After that, those were both necessary, or all four were necessary to calculate the notch sensitivity, which is the first equation here that is in terms of D, and also the Q shear is in terms of D as well. And then after that, we had to, well, actually, I guess I should note that the square root of A right here in the notch sensitivity is the Neuber constant. So then we used those values to calculate the fatigue stress concentration factors, which are here. And we also needed to find the polar and area moments of inertia. The polar moment of inertia was used within the formulas for finding the mid-range and alternating torques, which are a little farther down here. I then found the alternating and mid-range von Mises stresses, and so after that we could use the Marin equation here to find the endurance limit. And once all those variables were solved in terms of D, they could be plugged into the Goodman failure criteria here to calculate the ultimate factor of safety at the end. The next section pretty much highlights the equations that were used to find the critical shaft frequency in Hertz. The area of the cross section is needed when finding the mass per unit length. And mass per unit length equals density times area. We also use the area moment of inertia for a circular cross section, which is pi d to the 4th over 64. And ultimately, we calculated the critical shaft frequency in Hertz, and it's important to note that the 2 pi here changes it from radians per second to Hertz. And after those values were calculated, we were able to plot the graph for the safety factor versus diameter. And it's important here to note that the safety factor is highest at the smallest diameter. And if you can see right here, there's a small blip in the plot, and I'll explain that later on when I reference the MATLAB codes. Next we have the shaft frequency versus diameter plot, which basically shows that as the critical frequency gets higher, the shaft diameter has to get larger in order to compensate for the forces that are added on the shaft as it rotates. So the next part is actually solving for the optimum diameters, and without the design constraint, we came up with a value, or I came up with a value of 2.79 millimeters for the optimum diameter, and that was calculated using MATLAB, and I've shown here a snip of the output for what was shown in the output terminal in MATLAB. And then the second part here is the optimum diameter value with the constraint of at least 150 hertz as a critical shaft frequency, and that optimum D value was 23.5959 millimeters. And then to kind of wrap things up, I interpreted the solutions for why the results in 3 and 4 are different. So as a shaft rotates, a rotational deflection is created that is resisted by the rigidity of that shaft, which is represented as E times I. When the shaft reaches a critical frequency, the shaft starts to become unstable, which creates the opportunity for the shaft to break. When there's no constraint, the shaft diameter can be smaller because there are no additional forces on the shaft. When the shaft spins at its critical frequency, however, the diameter needs to be larger in order to compensate for the additional axial loading. So at the conclusion here is my appendix, which is the list of the MATLAB codes that I used for this project. I pretty much already summarized what's shown here, but as I said earlier, there was a blip in the factor of safety graph, and as you can see here in the if-else statement, the different value for KB needs to be set depending on the diameter. So if it's between 2.79 and 51 millimeters, the KB constant is 1.24 times d to the negative 0.107 power. And if it's greater than 51, the KB constant is 1.51 times d to the negative 0.157 power. And also here are the functions that I use to maximize the factor of safety, and also to see whether the critical shaft frequency is at least 150 hertz. So that about wraps things up. Oh, except for the code here for the plots of diameter versus factor of safety. Here's the code for that, and also here is the code for the diameter versus the critical shaft frequency plot, which I showed earlier. So that about wraps it up, and thank you for your time.